Okay, so we're going to fit a neural network to the digits data, and what I'm showing there on the top right is the small neural network that we're going to fit. That's by no means a deep network, okay? And now we're going to use the intensity symmetry features, so we've got two inputs, intensity and symmetry, and then of course the augmented one. So you see the input layer in blue has 3 nodes. The first node is the augmented one, and then there's one hidden layer, so there's just one hidden layer in red. Okay, and there are 10 hidden nodes, so there are 10 nodes in the hidden layer. So that hidden layer computes 10 perceptrons, but there are actually 11 red nodes because the first one is the augmented one. Okay, so we have the augmented one and then 10 perceptrons, and then the final layer is computing 1 perceptron of those. Okay, and then we fit this to the digits data. Okay, and look at what happens. Look at the awesome power of being able to cascade perceptrons, and this is nothing compared to the neural networks that people want to use in practice. Okay. So that kind of awesome power is what cascading allows us. Okay, and you look at the picture on the left, which shows how it has fit the digits data. Well, now we are experts. No one needs to tell us. Overfitting galore. Okay, so we need to do something about that. So now we have too much power. Remember when I gave you the nonlinear transform, I said it's like an 18-wheeler, and it's going to be hard to break it and stop it from overfitting. Well, this guy is, an order of magnitude worse. Okay, so we're going to have to deal with this overfitting. But on the right, I'm just showing you the comparison between, gradient descent, so the batch version of gradient descent, and the stochastic version of gradient descent, which is sort of what I focused on in the lecture, okay, where we compute for each data point the gradient of the derivative with respect to all the weights, and then update the weights, and then continue randomly picking data points. Okay, so that's the stochastic gradient descent. And the batch gradient descent is also doing the right thing. It's dropping, but just much more slowly. Okay. The other thing to observe, of course, is that the stochastic gradient descent, so what we're plotting is the full error, the in-sample error. And the stochastic gradient descent tries to minimize a little bit the error on a particular data point. So when you minimize the error on a particular data point, the error on the full data, oscillates. It doesn't necessarily go up. And that's what's that jiggly behavior. But on the whole, stochastic gradient descent looks very fast. Okay. So it shows you a couple of things. First, the awesome power of the cascaded perceptrons, the neural network. Even that small, shallow neural network can do wild things on this, digits data with just 2 inputs. Okay. The second is that how we choose to minimize the in-sample error, the optimization method we use, okay, does play a role, especially when we're talking about big data and big networks with lots of parameters. Okay. So in the next lecture, we will address both of these issues. We'll talk about the generalization issue, the overfitting issue, and we'll also talk a little bit about, improved, better methods for minimizing the in-sample error. Until then, checking out!